problem is on Chapter 2.5, Problem 73, page 250. The Mach number and half-angle formula. The Mach number m of a supersonic airplane is the ratio of its speed to the speed of sound. When an airplane travels faster than the speed of sound, the sound waves form a cone behind the airplane. The Mach number is related to the apex angle theta of the cone by sine of theta over 2 is equal to 1 over the Mach number.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
And now, back to the problem. Part A. Using a half-angle formula, rewrite the equation in terms of cosine of theta. So we know that our initial equation is sine of theta over 2 is equal to plus or minus the square root of 1 minus the cosine of theta over 2, which is also equal to 1 over the Mach number. We're going to take the right-hand side of this equation, and we're going to square both sides to get rid of the square root, thus giving us 1 minus the cosine of theta over 2 is equal to 1 over the Mach number squared. We'll then multiply both sides by 2m squared, canceling out the 2 and m squared respectively, and giving us m squared times 1 minus the cosine of theta is equal to 2. We'll then divide the Mach number squared by both sides, giving us 1 minus the cosine of theta is equal to 2 over the Mach number squared. Subtract the 1 from both sides, we have negative cosine of theta is equal to 2 over m squared minus 1. multiply both sides by negative 1, and we have cosine of theta is equal to 1 minus 2 over the Mach number squared. This brings us to our final answer here. Our equation in terms of cosine of theta is cosine of theta is equal to the Mach number squared minus 2 over the Mach number squared. Part B. Find the angle theta that corresponds to a Mach number of 1. So here we have our initial equation, cosine of theta is equal to m squared minus 2 over m squared. When m is equal to 1, the cosine of theta is equal to 1 minus 2 over 1. All that happened there was that we substituted a 1 for the m. The cosine of theta is equal to 1 minus 2 over 1, which is equal to negative 1. We know that when the cosine of theta is equal to negative 1, theta is equal to pi. Part C. Find the angle theta that corresponds to a Mach number of 4.5. So again, we're going to take our initial equation, cosine of theta is equal to m squared minus 2 over m squared. And once again, we're going to substitute a value in for m. This time, it's going to be 4.5. This will bring us to a cosine of theta is equal to 4.5 squared minus 2 over 4.5 squared. After simplifying, we come to this point, cosine of theta is equal to 0.901. After solving for theta, we find that theta is equal to about 0.4482 radians. Part D. The speed of sound is around 760 miles per hour. Determine the speed of an object with the Mach numbers from B and C. For Part B, we know that when m is equal to 1, the speed of the object over the speed of sound is equal to m. From this, we can derive this formula: the speed of the object over 760 miles per hour is equal to 1. After multiplying both sides by 760, we find that the speed of the object is equal to 760 miles per hour. Now for Part C. Again, we'll use the same formula. The speed of the object over the speed of sound is equal to m. We're going to substitute 4.5 for our m, bringing us to this equation. The speed of the object over 760 miles per hour is equal to 4.5. Multiply both sides by 760, and we find that our speed of the object is equal to 3,420 miles per hour at Mach 4.5.